You can see the screen?
Yes, sir.
Is screen visible to you? Yeah, okay. I hope the exam was okay for all of you.
Sir, due to network problem, I submitted 5 minutes late. Is it fine?
That's okay. I have considered, but everybody submitted, no?
Yes, sir.
Okay. I mean, the number of students whom I see on the ERP, all of them they submitted. Okay. So today I will introduce the new topic, that is the invariance in estimation problems. So basically it is started with certain decision theoretic concepts actually. So
Sir.
Yeah.
Sir, also, can you extend the deadline for the mega project? Like we also had exams in between, so.
I have given by Monday, no, 7th March. So
Yes, sir.
I gave you intentionally 7th March so that you can utilize Saturday, Sunday, and the last Saturday, Sunday also you got. So are you not able to finish?
Yes, sir. Due to exams and other events, we are unable to. Other assignments also. So.
Yes, sir.
Okay, maybe I can give maybe another 3 days. Is that okay? 10th March is okay? If I gave 10th March, is that okay? You can finish by 10th?
Sir, how is 14th possible?
It is possible, but then you will delay. I mean, then again, some students will say that we could not finish. I mean, then there is no end to it. So you have to come to a certain point where you have to actually put your effort and finish it. Will
So
10th not
make 14 hard deadline?
Okay, I'm writing it here. Okay.
Sir, also from next week, are the classes offline or online, sir?
We have been asked to take hybrid mode, so I don't know what is that. Probably those students who are in campus, they should go to the classroom. So how many of you are here in the campus? All of you are here?
Almost, sir.
Then you
Yes,
come
sir,
to the
almost.
class, then I will teach there. Then I think if all are here, then it is better to take in the class. Okay.
Yes, sir.
I can see some hands are raised, but some hands are not raised also. So I don't know. You can just do a survey. If all are here, then it will be just a simple offline class, and probably you would enjoy it more, and you will follow things. Because my next part is actually testing of hypothesis. So at least in that part, if you can do offline, it will be good. Okay. Because I don't know, online and then some people will be, I mean, some people will be offline and some people will be online. That I don't know, it doesn't look very convenient to me. But anyway, I'll try whatever is possible. So I'll check it on 7th, 8th, the facility in the classroom, and then I'll inform all of you. Okay. Okay, so let me start this invariance part. This is a new topic. Okay. The concept of invariance is based on symmetry. So actually, most of the statistical inference problems, they have some inherent symmetry. Now that symmetry could be with respect to translation. The symmetry could be with respect to scale. It could be with respect to linearity. It could be with respect to rotation. It could be with respect to permutation. Okay. So for example, if I consider, say, mean of the observation, so x1 plus x2 plus xn, no matter in what order I consider x1 plus x1, x2, xn, the sum or the mean remains the same. So it is invariant with respect to, you can say, permutations. Okay. So similarly, if you consider, say, median of the observations, if you consider the sample variance of the observations, so these are all having certain inherent symmetries. Of course, I just now mentioned permutation, but we will see that they also have certain invariance with respect to translation, with respect to scaling, with respect to linear transformation, with respect to orthogonal transformation, etc. So basically, in general, in the decision theoretic concept, that this invariance gave rise to what we call improved estimation procedures and, of course, improved testing procedures. So let me give a brief introduction to the general problem of decision theory, and then we will move to the specific concept here. So let x1, x2, xn be a random sample. Yeah, so from a population with distribution, we will use the notation that I have been using earlier. So something like p theta, theta belonging to, say, capital theta. So we are interested in estimating a parametric function say h theta. Okay. Let us consider the set possible values of h theta. So let us call it h theta, theta belonging to script theta. Okay. And take the smallest convex set containing z. Okay. Let us call it say script A. All right. So we usually restrict estimators of h theta to take values in A. This actually I explained to you when I was doing maximum likelihood estimation. I had considered problems like normal, mean, mu, and if mu is greater than or equal to mu naught, then our maximum likelihood estimator was getting modified to it is equal to maximum of x bar and 0. I had also considered that if mu lies between minus m to m, then the estimator was that if x bar lies between minus m to m, then we take it as it is. But if x bar is less than or equal to minus m, then we take minus m. And if x bar was greater than or equal to plus m, then we were taking it to be m. So I had explained this concept in detail in the maximum likelihood estimation, that whatever be the range of the values of the parameter, our estimator should lie in that. So saying it in this particular fashion in a very strict sense, I have defined it like this, that if I want to estimate h theta, then we consider the set of all values of h theta and take the smallest convex set containing it, and then we will restrict our attention to this. Okay, so this set A, in decision theory we call it action space. This one is called parameter space, and the set of values of x1, x2, xn, that is called sample space. So in a general statistical inference, we have three spaces: sample space, parameter space, and the action space. Now let us go back to the concept of efficiency. I said that an unbiased estimator, or in general an estimator T1 is better than an estimator T2 if the mean squared error of T1 is less than or equal to the mean squared error of T2. What is mean squared error? It is expected value of T1 minus g theta square and expected value of T2 minus g theta square. That means I am considering the error as estimator minus the parameter value, and then I am squaring it. Okay, and then I take expectation value of it. So now this concept you can extend to other kind of functions also. In place of absolute error, mean squared error, I can take absolute error, I can take log squared error, and so on. There can be various kind of things. So in general, we define the concept of loss. Okay, let the loss in estimating h theta by A. So A is certain thing by which I will say this is an estimator of h theta. So we denote it by L theta A. So for example, I can consider L theta A is equal to h theta minus A square. So this is squared error. Okay, I can consider, so let me put L1, L2 and so on. This could be say mod of h theta minus A. Of course, I can write it as A minus h theta square, and here mod of A minus h theta, because these are symmetric with respect to the sign, like L theta A. So third one I can write it as say log of h theta by A. So in general, I am having an estimator. So an estimator T of h theta has a risk function. So I called this as the loss function L theta A. All right, and this is risk function. So risk function is denoted by R theta T, that is equal to expectation of L theta T of x. Okay, so we take the expectation of this. So for example, if I am taking L1 here, then this becomes nothing but the mean squared error. If I consider this to be L2, then this will become absolute error. So mean absolute error and so on. Okay. Is this concept clear to you? Then I will proceed to the some example to illustrate this function here. Is this concept of loss function and risk function understandable to all of you?
Yes, sir.
Yes, sir.
So let us consider say a random sample. Let me start with the simplest example. Normal distribution, say with mean mu and variance 1. So mu is any real number in general. And I take the loss function to be L1. That is mu minus A square. Okay. In estimating mu by a loss function is mu minus a square. That is the squared error. So we know, for example, x bar is an estimator. Okay, t is equal to x bar. Actually, we have shown this is UMVUE. It is also MLE. It is also method of moments estimator for this problem. These things we have already shown. Okay. So I want to consider what is the risk of this estimator. That is expectation of mu minus x bar square. This is nothing but the variance of x bar, that is 1 by n. Okay, is that clear? I think.
Yes, sir.
Now, if we had normal mu sigma square, okay, see here it is a constant 1 by n, it is coming. But if I have normal mu sigma square, then also we have shown, then also t is UMVUE, MLE as well as MME, etc. But now what would be the risk function here? That is variance of x bar. Now it has become sigma square by n. Now this is a function of parameter, sigma square, because sigma can take any value. Sigma can be 1.2, sigma can be 3, sigma can be 9, sigma can be 100 and so on. This can take various values. The range of sigma is taken to be 0 to infinity. So sigma square by n, it can vary. Actually, if you want to plot it, so on this side if I have sigma square and on this side I am considering r mu t, then starting from 0 it will keep on increasing actually, because sigma square it's a linear function, so it will go like that. So in general, because risk function will be a function of parameters, sometimes it can be a constant like in this particular problem, but in general it will be a function of parameters. In general, risk function depends on parameter theta. So suppose I consider theta to be one-dimensional parameter. In case theta is a scalar parameter, we can consider plotting like I have done the plotting here. For any estimator, delta of h theta. Okay. So if you consider like this, let me consider like this. And here I drew from the positive side, but it can be negative or anything. So in general, you can consider, say, some kind of plot like this. It can be like this. It can be like this. Okay. And of course, there can be various kind of curves can be possible. Okay. Suppose I say this is risk function of the estimator, say delta 1. This is risk function of the estimator delta 2. This is risk function of the estimator, say delta 3. This is risk function of the estimator delta 4 and so on. So what do you observe? You observe that some estimator, suppose I consider this as the point. If I take this point theta naught, then at this point r theta delta naught is having the lowest value compared to other estimators. Suppose I take this point. If I take this point, then at this point the estimator delta 3, that is having the lowest risk value. Suppose I take this point, At this point, if I consider r theta delta 4 is having the lowest value. So at different parameter points, different estimators may have the minimum risk value. So when our criteria is to say that which estimator is the best, I will say there is no best. Okay. So let me write it here. We define an estimator. So these are decision theoretic concepts, and I am introducing it here because you are doing a course on inference, and currently all the considerations in general in any area of science and technology, it is based on the best decision. Okay, what is the best decision? So what we conclude that there is no best. Okay, I will just explain it through some other real example also. Okay, so an estimator delta 1 to be better than estimator delta 2 for estimating, say, parametric function h theta if r theta delta 1 is less than or equal to r theta delta 2 for all parameter configurations with strict inequality at least for some theta. Okay. So this is actually a generalization of the efficient estimator, that we said that the estimator T1 is more efficient than T2 if the mean squared error of T1 was less than the mean squared error of T2, or in the terms of unbiased estimator if the variance of T1 was less than the or equal to the variance of T2. So this is an extension of that definition in a general decision theoretic setup. So if for a given estimator, say delta naught, there exists an estimator, say delta 1, such that delta 1 is better than delta naught, then we say that estimator delta naught is inadmissible. That means delta 1 is better than delta naught, so delta naught is inadmissible, means I can forget about delta naught. For my inference purpose, delta 1 should be considered because delta 1 is better than delta naught, so I can discard delta naught. Okay. If there is no estimator better than delta naught, then delta naught is said to be admissible estimator. So I think you understand this concept. By admissibility, we mean that there is nothing which is better than that. So this is a desirable thing. Admissibility is a desirable property. Because if an estimator is inadmissible, then there is something better than that. So therefore, I can forget about the previous one. I can discard it. I can consider only the good ones. Okay. So admissibility is a desirable property in decision theory. Okay. However, I am putting some general comment. In a general estimation problem, there is no estimator which has minimum risk at all parameter points. Now this is an interesting statement here, and it is having very deep significance. So whatever be the estimation problem, there is no estimator which is the best among all. For example, just now I gave you X bar as the UMV, UE, MLE and method of moments estimator for estimating the mean of a normal distribution. What does it mean that X bar is better than all other available estimators? The answer is no. Actually, later on I will also mention that X bar is an admissible estimator in this problem. But there can be more than one admissible estimator. In fact, there will be infinitely many admissible estimators also. So therefore, there is nothing which is best. So what we do in decision theory, then we introduce additional concepts to choose certain property by which one sorry. By which one admissible estimator can be preferred over another admissible estimator. This point I will illustrate with respect to one loss function here. Suppose I am taking loss function to be the squared error, okay, and I choose for points say theta 1, theta 2 and so on. Let us define estimators in the fashion estimator also to be theta I. Okay, then what is the risk function of Ti? That is theta minus theta I square, because these are constant estimator. So it is, there is nothing like expectation. I mean, this value is constant here. So obviously this is equal to 0 if theta is equal to theta I, and it is greater than 0 if theta is not equal to theta I. So if I plot the risk functions of, so suppose this is 0, so it will be like this. Suppose I consider so if I am considering risk of T2, risk of T1, risk of T0, etc. You can see that the risk of estimator T0 is minimum at theta naught, risk of T1 is minimum at theta 1, risk of T2 is minimum at theta 2. So there is nothing which is best, because if I take arbitrary point here you see at this point, see there will be another estimator. Suppose this point is say eta, then I can define estimator to be eta, then that will have minimum risk value at this point. So it shows that, so there is no best, okay. Now this is a very deep, this concept has a deep significance in general in the real life situation also. So as I mentioned to you that any practical problem can be reduced to a statistical decision problem. So for example, you want to estimate the risk. Say for example, if you are a student studying in Ukraine, and on the 15th of February there is an advisory by the government that the students should leave as early as possible from there. Now a student who is there, he has to weigh his options based on the situation which is evolving. That means whether, say, Russia will attack Ukraine. If it attacks, then whether there will be a risk to him or not. And therefore, various kind of decisions are taken. Some students, they left immediately, some students could not leave, and then they have been facing a lot of hardships, and including one student who actually passed away due to getting involved in the firing from one of the forces. So you can see the effect here. Whatever decision you take, there is a risk involved there. Like some students who left immediately, now you can see that he was beneficial or he benefited, and the student who did not leave, they had to spend a lot of money or resources, and then they could come back, and one student who lost his life. So whose risk is the smallest, isn't it? So whatever decision you take, there is a problem there. So the theory of optimal decision rules is based on this concept only, that we try to consider different possibilities. For every different possibility, what is the best possible rule, and we minimize that one. That is called minimaxity. So I will come to that a little later. Right now, I just wanted to introduce this from a deep philosophical point of view, that in real life situations, if you are considering decision theory, then there is no best choice. Okay. Is that point clear to all of you?
Yes.
Actually, I'm not talking about the general decision theory. I'm talking about only the estimation thing. So in estimation, we have already seen concept of, for example, unbiasedness. So if we have unbiased estimation, then that is one kind of restriction in the class of estimators, and then we try to find out the minimum variance unbiased estimator. So within a class, we can find the best. Among all of them, it is difficult to find. I mean, it is actually not possible to find the best. So we employ additional criteria such as unbiasedness, invariance, etc., to restrict the class of available decision rules. Okay, so let G denote a group of transformations okay, from X means the set of values of Xi's, okay, and the group operation we are taking to be composition of functions. I think you must be doing the course on algebra also. Some of you are doing the course on algebra or discrete mathematics you have done.
Sir, we have done only discrete structures.
Yeah, so there I think, see, composition of function probably you had in your class 11, 12 also, isn't it?
Yes, sir.
Okay, so I think that should not be difficulty. So, because on a group of transformation, you should have a composition. That means under what you are, I mean, group operations are like plus, product, and so on. I mean, so there can be anything. I mean, like if I'm considering functional functions, then I'm considering composition as the group operation. Okay, so the identity transformation is denoted by E. So Ex is equal to X for all X. And we assume that all the transformations in G are 1, 1 and on 2. Okay. So that means G inverse will exist. Okay. We had the family of distributions. So we say that the family of distributions is invariant. Under the group G, if for every G belonging to G and every theta belonging to theta, there exists a unique theta prime belonging to theta such that whenever the distribution of X is p theta, then the distribution of Gx is p theta prime. Okay. I'll introduce with respect to some example so that you can easily understand it. So this theta prime we will denote by some G theta. So I will put G bar theta, okay, in place of G, because G is on sample space. Now it is on the parameter space. Okay. So we have the following statement that probability that Gx belongs to A is same as probability of X belongs to A, where it is G bar theta. In terms of expectation, this condition becomes phi of, say, Gx is equal to expectation of phi x G bar theta. So basically what I am saying is that if x follows p theta, then gx follows p theta prime, that is p g bar theta. So let me just explain through some example here. Suppose I am considering say x1, x2, xn following normal theta 1. Okay, so theta belongs to say the set of real numbers and I am considering the group of transformations to be GC of x1, x2, xn is equal to x1 plus c and so on xn plus c. In fact, I can explain through one variable itself and then we can go to the n variables. It is better to consider one just for the sake of convenience here. Let me put it for 1 and then we can write for general. So that is equal to say x plus c, and where this c can be any real number. So this is a group. Then G is a group, because if I consider say G of C1 and G of C2, then this is equal to G of C1 x plus C2, that is equal to x plus C2 plus C1. So if C1, C2 are real, then C1 plus C2 is also a real. So this is G of C1 plus C2. Okay, so the composition operation holds here. Okay, now if we consider that means the closure property is okay. If we consider identity element, C is equal to 0 is identity, because if you add 0 you get the same term. If you consider associative property, then that also holds GC1, GC2, GC3. So in any order if I take, then they are holding. Identity element is there, inverse element is there. For C, minus C gives the inverse element. So G is a group. So this is a group here. So now let us see on the set of probability distributions here, that is the normal theta 1, whether this family of distributions is invariant. The answer is yes, because if I consider GCX, then GCX is x plus c. This follows normal theta plus c 1. So if theta is real, theta plus c is also real. So the family of distributions is also invariant. Under this group. And what is GC bar theta? That is theta plus c. As I think up to this it is clear to all of you. I have considered the translation group, or you can say location group.
Sir,
Yes.
sir, how minus C gives the inverse element?
So if I consider, say, what is the definition of inverse element? That if I apply it on the transformation, I should get identity, isn't it? So if I consider, say, GC, say GCX, that is x plus c. So on this, if I apply g minus cx, that means g of minus c of this, okay, then what I will get?
Okay, yes, sir.
X plus c minus c, that is x itself, that is e of x. So therefore this is inverse.
Okay,
And this also belongs for every, because here I have taken in the group definition, all c's are considered here. So therefore, for every c, minus c is also there. That is g of minus c belongs to the group. So it is closed under the identity and inverse. All right. So I will state the result in the form of a lemma or a theorem. So suppose let me call it a lemma here. If a family of distributions p theta is invariant under a group G of transformations, then G bar is a group of so this is actually, it is called induced by G. Okay, G bar is said to be induced group by this one. So on the parameter space, this is also a group. Let G1 and G2 be two groups. A function alpha from G1 to G2 is called homomorphism if alpha xy is equal to alpha x into alpha y for all xy. And isomorphism if a homomorphism is 1-to-1. It is said to be isomorphism. Actually, from G we have come to G bar, but this is not an isomorphism. Actually, it is homomorphism. So G to G bar, this induction, this is homomorphism. But not necessarily an isomorphism. Sometimes it can be isomorphism, but not everywhere. So what is the purpose of defining this group of transformations, etc.? I want to construct, like earlier I defined unbiased estimators. Similarly, I want to introduce invariant estimator. Okay. So if I have invariant estimator, then I can try to find out the best in the class. Okay. In the class of estimators, what is the invariant estimators? What is the best invariant estimator? So that is another way of looking at the restricted class of estimators, because I mentioned to you that in general, overall, we cannot find the best. Okay. So under certain constraints or restriction, we can find the best. So what is an invariant estimation problem? So you have x, okay, x belongs to x. Then you have x follows p theta, theta belongs to script theta, and estimation problem is of estimating some h theta, and a is the estimation space or action space. That is the smallest convex set containing h theta. So these are some of the basic terminology. You have the sample space, you have the parameter space, you have the action space. So the estimation problem is to choose a point in A. With respect to this, there is a loss function associated. L theta A. Okay. So usually it is a function from theta cross A to real line. Then we will say that the estimation problem is invariant under the group G if for every G belonging to G and A belonging to script A, there exists a unique A prime belonging to A such that L theta A is equal to L G bar theta A prime for all theta. That means the loss function does not change the value at a equivalent point. That means whatever is the loss in estimating theta h theta by A, it remains the same if I transform theta by G bar theta, then corresponding A is transformed to some A prime such that the loss function remains same or invariant. So we denote by A prime to be G tilde A. So I'm putting another notation. Earlier I used bar, now I'm using tilde notation. So this G tilde is a transformation of A into itself. So the group of transformations acting on the action space that is denoted by G tilde. So this is another induced group of transformations by G on the estimation space, and we have the following lemma. Again, these lemmas I am not writing down the proofs. Those who are interested, you can look at the book by Rohatgi, or by, I will write another reference here. Probably I have already given in the list of books which I gave for this course. And once again, G to G tilde is a homomorphism but not an isomorphism. Okay, so is this discussion clear? Now I will give some example of these groups of transformations here, although I gave just now for the translation group. Is it okay, or do you have any questions till now?
It's fine, sir.
Okay, so maybe I think we can have a break for 5-6 minutes, and then I will move over to the examples and then other properties of this invariant estimators. Okay, so I'll give a break for 5 minutes. So I start with the examples of invariant estimation problems.
Sir,
Yes. Yes.
sir, G as G tilde is a homomorphism, you said.
Yeah, but not an isomorphism.
Is it not necessary or it is not always?
Not necessarily. Yeah. Not necessarily. So sometimes it can be. Yeah.
Okay, sir.
So suppose I have a binomial random variable. Okay. So in n trials, we have obtained x number of successes, where p is the probability, and we have estimation problem for say p itself. We want to estimate the proportion p. We want to check whether this problem is invariant under certain group. So I consider a group consisting of two elements, identity element and G, where G is defined to be that n minus x. X goes to n minus x. Then what is the distribution of Gx? That will follow binomial, because that is the number of failures. So it is also binomial. And 1 minus p is also between 0 and 1. Okay. So the family of binomial distributions is invariant under this group. That is binomial NP, where P is between 0 and 1, is invariant. Under this group G. So what is the induced transformation? GP goes to 1 minus P. So if we want to consider the invariance of the estimation problem, I should have invariance of the loss. So L G bar P A prime, that is equal to G bar P minus A prime square, that is equal to, so this is 1 minus P minus A prime square, that should be same as P minus A square. Okay, that is what we want. Okay, this implies that A prime, that is G tilde A, is equal to 1 minus A. So therefore we are able to find a point in the action space. See, what is the action space here? Action space is also the closed interval 0 to 1, because the parameter space is closed interval 0 to 1. So the smallest convex set containing this is also the same. So this belongs to same, this one. So this problem is invariant. Of course, invariant under a given group. Okay. I mean, for every problem, you have to find out a different group of transformation. It is not necessarily the same in all the problems. Okay, is this example clear?
Yes, sir.
Let us take another So I consider uniform 0 theta. I am taking only one observation for convenience because I just want to demonstrate the invariance here. In general, you will have n observations. So L theta A, that is equal to A by theta minus 1 square. So I am not taking A minus theta square, but I am also dividing it by theta. So this is slightly different. It is called a scale invariant loss function. Okay. It is a modification of the squared error loss function. So we consider the group scale transformations. I am putting GS here. So GC, that is GCX is equal to C times X, where C is any positive real number. Again, you can see that this is a proper group in the sense that if I consider composition, that is G of C1 on G of C2X, then that is equal to C1 C2X, that is G of C1 C2X. So this is closed, closure property is satisfied. Associativity is of course obvious. C is equal to 1 is the identity element. And C prime is equal to 1 by C is inverse element. Okay. So this is a proper group. We call it actually a scale group of transformations. So let us see this problem of uniform 0 theta, whether it is invariant. So what is the probability density function of X? Let us consider, say, Y is equal to Cx. Then what is the distribution of Y? Just by the Jacobian method, you can immediately write. So this is 1 by C theta, 0 less than Y less than C theta, and 0 otherwise. So you can see that this theta has been replaced by this, that is Y follows uniform 0 C theta. So if theta is positive real, then C theta is also positive real because C is positive. So the family of distributions is invariant. You have GC bar theta is equal to C theta. So the family of uniform distributions, uniform 0 theta, theta greater than 0, is invariant under the group GS, a scale group here. Suppose I am considering estimation of theta. I have taken the loss function to be A by theta minus 1 whole square here. So if I consider, say, L GC bar theta A prime, that is L of C theta A prime, that is A prime by C theta minus 1 square. If I want it to be equal to A by theta minus 1 square, then we should have A prime is equal to CA, that is GC tilde A. That means the estimator should also shift by, that means it should also get scaled by C. So the estimation problem is invariant under this group. I hope it is clear to all of you.
Yes, sir.
Let me take another example. X1, X2, Xn follows normal mu sigma square. Okay. I am considering the loss function, say L1 mu A is equal to mu minus A by sigma square. L2 sigma square A is equal to A by sigma square minus 1 whole square. Okay, let me consider these two at the moment and then consider something. So consider the group of transformations. So I'm writing GBCX. So BCX is BX plus C, where B is non-zero and C is any real number. Okay. This is called group of linear terms of X or group of affine transformations. Actually, in statistical terminology, we call it affine, but of course it is a linear transformation, but it is one-dimensional linear transformation. In general, you will have matrix AX plus B kind of thing, but that is for the multivariate normal. Since you are not much familiar with the multivariate normal notation, so I will not introduce that one at this moment. I will give only the simplest one here, univariate normal distribution. Okay. Now under this group, what happens? Let us look at it. So X follows normal mu sigma square. What is the distribution of GBCX? Suppose I call it Y, then that is BX plus C. Because of the linearity property of the normal distribution, this follows normal B mu plus C, B square sigma square. So in the normal distribution, mean is a real number and variance is a positive number. So even if you put B mu plus C for whatever value of B and whatever value of C, this remains a real number and this remains a positive real. So the family of distributions is invariant. This is a real number, this is positive. So the family of normal distributions that is normal mu sigma square is invariant. Actually, we can put sigma positive rather than sigma square because the standard deviation is also positive under group GA. And from here, you have also looked at what is the transformed. The mu goes to B mu plus C and sigma goes to B sigma. So we can put it in this particular fashion. G tilde of mu, not tilde, it is G bar. G bar of mu sigma square, that is B mu plus C and B square sigma square. So the transformation also you can see. Now I have put here two estimation problems. One is the estimation of mu and another is estimation of sigma square. Okay. Let us see the form or the effect on the action space or in the estimators, what will be happening. So for L1, you will have L1. Now, if I am considering this mu, see this function we can write in a little bit general form. Although it is estimation of mu and this is estimation of sigma square, you can note here that here both the parameters mu and sigma are appearing. Here, of course, only sigma square is appearing. So in general, we can actually modify the notation of the loss function itself. We can put it in a little bit general form because L theta A we were writing. So we can put mu sigma square here, L1, and this is of course L2 sigma square. So what we want now, L1 B mu plus C B square sigma square A prime. So we want it to be B mu plus C minus A prime whole square by B square sigma square. This one, if I want to be equal to mu minus A by sigma square, that is L mu A, then we should have A prime is equal to B A plus C. So this is the form, that is G tilde of the action space A here, it is B A plus C. That means the same linear transformation should be applied to estimator of mu. Let us look at on L2 what happens. So let me put here G1 because this is with respect to this loss function. So for L2 what happens? For L2 it is B square sigma square A prime, that is equal to A prime by B square sigma square minus 1 whole square. And if I want this to be equal to A by sigma square minus 1 whole square, then we must have A prime is equal to B square A. Okay, so this is your G2 tilde A. So we conclude that both estimation problems are invariant under the group GA. So is it clear to all of you?
Yes, sir.
So now this condition that G tilde A, that gives us that what should be the form of an invariant estimator. That means an estimator which satisfies this invariance property. So we will give a new name to it and try to see that how to implement such a thing. Okay. Equivariant estimator. So an estimator Tx is said to be equivariant under G if T of Gx is equal to G of Tx. Now, when it is G is applied on the sample space, it is G, but if it is applied on the estimator, it is G tilde. Okay, for all x and for all g. So an equivalent estimator satisfies this condition. Okay. So let me just explain through the exercises that we have just now seen. Binomial problem, then the normal problem, etc. Let us see what happens here. So what would be the condition here in the binomial? T of Gx is equal to G of Tx. Actually, in binomial distribution, we have taken only one observation, and only identity element is there, and one element G is there, where Gx was defined to be n minus x. Okay. So this condition is easy here, and this is true for all x 0, 1 to n. And so if I take G to be identity, then it is trivially true, and Gx is equal to n minus x. That part we have to check that what condition it will give me. Okay. So this gives us T of n minus x is equal to 1 minus Tx, because G tilde A was 1 minus A for this problem. That means we should have Tx plus T of n minus x is equal to 1 for x is equal to 0, 1 to n. So this is the condition of an equivariant estimator. Okay. For example, if I take x by n, if you remember, this was UMV UE, this is unbiased, consistent, it was MLE, etc. So this is a good estimator. Okay. Is it invariant also or equivariant also? So Tx becomes x by n, and n minus x by n, that is equal to 1, is satisfied here. So this is an equivariant estimator under this group here. Okay.
Yes, sir.
Similarly, we can check in the uniform example and in the normal example, but before that I'll talk about some properties. Okay. Again, we introduce this equivalence here. Okay. Equivalence we had talked about in the concept of minimal sufficiency. So similar thing I talk here. So 2 points theta 1, theta 2 belonging to script theta. They are said to be equivariant if there exists G bar belonging to G bar such that theta 2 is equal to G bar theta 1. That means if from theta 1 I can transform to theta 2 under certain induced transformation, then the points are said to be equivalent. Okay. So it can be easily checked that this is an equivalence relation. Why it is an equivalence relation? It is reflexive because every point is related to itself. Okay. I think I have made some mistake here. Yeah, this is equivalent, not equivalent. Yeah, equivalent. Yeah, there is a writing mistake here. This is equivalent, so this is an equivalence relation. So it is reflexive because if I take G to be identity, then every point is related to itself, so it becomes reflexive. Then symmetry is there because inverse exists, so it is symmetric. And because of the composition operation that it is closed, it is also transitive. So if I take theta 1 related to theta 2 related to theta 3, then theta 3 is related to theta 1 by G bar and say G1 bar, G2 bar, etc. I don't think I have to explain it too much. So it partitions the parameter theta into equivalence classes. So these equivalence classes, they are called orbits. Then the risk function of an equivariant estimator is constant on the orbits. This is actually a very significant statement, because if you have constant on the orbits and in certain decision problem or in certain estimation problem, if you have a single orbit, that means it's a transitive group, for example the translation group or the scale group. In such cases, the risk function of an equivariant estimator is completely constant, and then you can minimize the risk function with respect to that constant so that you get the best equivariant estimator. So this gives a partial solution of the optimality in the terms of optimal estimation. I mentioned to you that in the complete class of estimators, there is no best estimator. However, you can apply additional restrictions and take the best choice within those restricted classes of estimators. One is the unbiased estimation that we have already seen, how to find out the uniformly minimum variance unbiased estimator using two different approaches. One was the approach of the lower bounds. If the lower bound of an estimator achieves the if the variance of an estimator is equal to the lower bound, then it is the minimum variance unbiased estimator. Of course, that approach has certain limitations. It cannot be applied all the time. So if you have a complete and sufficient statistics, then any function of the complete sufficient statistics is UMV UE of its expectation. That result is widely applicable whenever you have a complete and sufficient statistic available. So this one, now I am talking about the best equivariance here. Let me state it in the form of a theorem here. Let Tx be an equivariant estimator in an invariant decision problem. I am not writing the full decision problem. Full decision problem means there is a sample space, there is a parameter space, there is an action space, there is a loss function, there is a group of transformations. So all those things are understood that they are there. That is x, theta, a, l, theta, a, and g. These are there. Okay, these things should be there. Then r, theta, t. It is equal to r g bar theta t for all g bar and for all theta. That means on the orbits, the risk function does not change. So if there is a single orbit, you will be able to find the best. So this gives a some sort of optimality criteria or optimal solution in certain estimation problems wherever it is applicable. So let me give a basic proof of this. Of course, you are not supposed to like mug up all these things because it involves certain properties here which you have not done at this moment in your career. You are still a second year student, but still for the sake of completeness, let me mention it here. So I am writing down the risk function of the estimator t at the point theta. So here what we do, we apply the first invariance, that is we can put it here g bar theta and g tilde tx. That means I have implemented the invariance of the loss function. Okay, that property I have implemented here. Now in the next step, what we do, we implement the equivariance condition of the estimator. So this will become t of gx. So this is due to equivariance of t. Okay. Now we implement the invariance of the family of distributions, because if x has a distribution p theta, then gx has a distribution g bar theta. So I can modify this here and I can write here this as expectation of g bar theta L g bar theta t of x. Okay, so gx I have put as x again. You can say it y, but then y has the parameter g bar theta. So I have implemented here invariance of family of distributions. So this is nothing but r g bar theta t. So the risk function of an equivariant estimator is constant on the orbits. So let me give some examples here. Let us take say x1, x2, xn following normal theta 1. Okay, just the simplest estimation problem. And I am considering the translation group. That is, let me put group translation as GT. That is G C of x is equal to x plus C. C is any real. One thing now again, let us utilize here. In place of considering all the observations x1, x2, xn, I can restrict my attention to the estimators based on x bar itself. Why? Because of the Rao-Blackwell theorem. Because we had proved that if there is any estimator of theta, then I can construct an estimator which is better than that estimator if I take conditional expectation with respect to the sufficient statistics. So there is no need to consider all x1, x2, xn now. So we restrict our attention. Actually, that simplifies the problem, because rather than considering all, let us just consider x bar. So we restrict attention to estimators based on x bar only. Okay. Now it is easy to look at the, so what happens to this one if I consider GC x bar, that is x bar plus C, because if all the observations are shifted by C, the mean is also shifted by C. So what is the distribution of x bar plus C? That is normal theta plus C1. Okay, so if theta is real, then C is real, then theta plus C is also real. Okay, so the family of distributions is invariant. That is normal theta 1 is invariant. Actually, for x bar, it will become 1 by n here in place of this one, because x bar follows normal theta 1 by n. Okay, so you can just modify it and it doesn't create any problem here. Here I can write this thing. Under the group GT. Let us consider, say, loss function to be squared error, or I can take any increasing function of distance. Actually, I can consider any function of this. Okay, but for convenience, let me take this one here. So what would be the form of equivariant estimator? An equivariant estimator based on x bar will satisfy. So you will have theta minus T x bar equal to theta plus C minus, so whatever transformation you are putting, T x bar plus C. Okay. I can put it here like this, so that in the next step you can understand this. Okay, I can remove these brackets here just for convenience. This implies that Tx bar plus C should be equal to Tx bar plus C for all x bar, for all C. So choose C is equal to minus x bar. Then this will give me Tx bar is equal to x bar plus a constant, because this will become T0, that is equal to x bar plus some constant K. So this is the, so an translation equivariant estimator of theta based on x bar is of the form, I can just write it as a delta k x bar is equal to x bar plus k, where k is any real number. So this is a single orbit here, because any real number can be approached from any other real number by translation. So the risk function of this estimator will be actually constant. So therefore I can consider minimization here. So let us consider the risk function of delta k, that is expectation of theta minus x bar minus k square. So what it is equal to? That is equal to expectation of x bar minus theta square plus k square minus, or you can say plus 2k expectation of x bar minus theta. Okay, so this is 1 by n plus k square plus this is 0. So I don't have to write this term here. Since this is coming k square, so what is the minimum value? It is at k equal to 0. So delta 0 x bar, that is equal to x bar is the best location or translation equivariant estimator. I hope the exercise is clear to you. Is it clear to you?
Yes, sir.
Okay, so in a similar way, you can look at other problems. I will take up other estimation problems in normal distribution as well as in some other distributions, and we will try to find out wherever possible the best equivariant estimator under a particular group. Of course, for different problems, different groups have to be considered. So this is some sort of optimality solution here. And here, of course, in this particular problem, you again get x bar. But you will see in other cases, it is not necessarily x bar all the time. Some different things can also come there. And in fact, you will observe that some other things will come. Okay. So if this is clear to you, then I will stop today's class at this point. Tomorrow, actually, I will be skipping the class due to some engagement at that. Exactly at that point of time, I have some work here, so I will not be able to take the class. In the next week, I will take one additional class. So you can tell me your preferable time and maybe day and time so that I can take one extra class. You need not respond immediately, but in MS Teams, you can put it there. Okay. In the MS Teams, you decide a comfortable time, which is convenient to all of you. And please complete the mega project that I have given by 14th March. Okay, I will not increase any date after that. Is that okay?
Yes.
Yes, sir.
Okay, so please give me a slot for one extra class in the next week, and the hard deadline for this one is there. And tomorrow I will skip the class. Okay.
Okay, sir.
Okay, sir.